In this video, I will teach you how to find limits using L'Hopital's rule, which is a way of finding limits using derivatives. If you appreciate the content, please give it a like. But first, a quick review. Say you're taking the limit of a rational expression. So you have a function in the numerator and a function in the denominator. If direct substitution gives you 0 in the numerator and some number in the denominator, like 13, then the value of the limit is 0, because it's just like 0 divided by 13. However, if direct substitution gives you a number in the numerator and 0 in the denominator, then the limit does not exist. In fact, I should not put an equal sign there. Never say equals and then dne. So I'm going to write dne, which stands for does not exist, because you can't divide by 0. On the other hand, if direct substitution gives us 0 in the numerator and 0 in the denominator, this tells us nothing about the limit. It might exist, it might not exist, it could be 0, it could be anything. We have to keep going using other techniques. Most of the limit problems fall into this third category. What if you're taking the limit as x approaches infinity, and you find that the numerator is approaching infinity, while the denominator is approaching some constant? If the numerator keeps getting bigger and bigger, while the denominator approaches a constant, then the overall value of the expression just gets bigger and bigger. So the limit is infinity, or you can simply say the limit does not exist, dne. What if the situation is reversed and the numerator is approaching a constant while the denominator is approaching infinity? If the numerator stays small while the denominator gets bigger and bigger and bigger, the overall value of the fraction gets smaller and smaller and smaller, closer and closer to 0. So the limit is equal to 0. However, if the numerator and denominator are both approaching infinity, this tells us nothing about the limit. You have to keep going using other techniques. What if you're taking the limit of the product of two functions, and the first function is approaching 0, while the second function is approaching some constant, like 13? This works just like you would think. The limit is 0. Think 0 times 13 is 0. But what if one function is approaching infinity while the other function is approaching a constant? If you are multiplying two functions and the value of one function basically remains constant, while the other function gets bigger and bigger and bigger, the overall value of the expression gets bigger and bigger and bigger. So the limit is approaching infinity, or you can say the limit does not exist. But what if one factor is approaching 0 while the other factor is approaching infinity? This actually tells us nothing about the limit. You have to keep going using other techniques. You might be thinking, well, 0 times any number is going to be 0, so your guess might have been that the limit would be 0. But that's wrong, because f of x is not actually 0. It's approaching 0. It's something that's getting smaller and smaller, but it might be 1 over 5, 1 over 10, 1 over 100, 1 over 1,000. It's not 0. So this is more like a battle or a race. One factor is getting smaller and smaller and smaller, while the other factor is getting bigger and bigger and bigger. Who wins? We don't know. If you are taking the limit of a rational expression, so a function in the numerator and a function in the denominator, sometimes you can use L'Hopital's rule to find the limit, but there are some preconditions. The first one is that the numerator and the denominator are both continuous functions. Also, for L'Hopital's rule to apply, the numerator and denominator must both be approaching 0, or they must both be approaching infinity. If all this is true, then L'Hopital's rule says the limit of f over g is equal to the limit of f prime over g prime. In other words, you can take the derivative of the numerator and denominator separately without changing the limit. Let's convince ourselves that L'Hopital's rule actually works by first finding this limit using the algebraic techniques that we learned back in Unit 1. We always try direct substitution first, but this gives us 0 in the numerator and 0 in the denominator, so we have to keep going. Factoring the numerator gives us this, and we learned that you can cancel out common factors like this without changing the value of the limit. We can solve this limit by direct substitution. Plugging in 6 for x, we get 6 minus 1, which is 5. Now let's find the same limit using L'Hopital's rule. Always keep in mind that L'Hopital's rule has preconditions. The numerator and denominator must both be continuous functions. But these are both polynomials, and polynomials are continuous. Also, the numerator and denominator must both be approaching 0, or they must both be approaching infinity. So, showing that the numerator approaches 0 and the denominator approaches 0, like I did here with arrows, is actually mandatory for using L'Hopital's rule. So, do not skip this. Always show arrow 0, arrow 0, before applying L'Hopital's rule. L'Hopital's rule says we can take the derivative of the numerator and the derivative of the denominator without changing the value of the limit. So let's go term by term. The derivative of x squared is 2x, and the derivative of negative 7x is negative 7. The derivative of x minus 6 is 1. So notice how taking the derivative makes the expression simpler. That's the power of L'Hopital's rule. We can evaluate this limit by direct substitution. Plugging in 6 for x, we get this, but 12 minus 7 is 5. Same as we got before. On a problem like this, the old way is just as easy as L'Hopital's rule, so there's nothing wrong with doing it the old way. But we will quickly see problems that either can only be solved by L'Hopital's rule or will be way easier to solve using L'Hopital's rule. For example, on this limit, there are no algebraic methods that will allow us to find the limit. Direct substitution gives us 0 in the numerator and 0 in the denominator. So L'Hopital's rule does apply because both functions are continuous. So according to L'Hopital's rule, we can take the derivative of the numerator and the denominator without changing the limit. Memorized rule, the derivative of sine x is cosine x, and the derivative of x is 1, which I'm not going to write. We can now evaluate this limit by direct substitution. Plugging in 0 for x, we have the cosine of 0, and at 0 radians, which is like right here on the unit circle, cosine is the x value, which is 1. I'm going to say this over and over again for emphasis. This part right here, where I wrote arrow 0, arrow 0, this is mandatory for L'Hopital's rule. Make sure you show this because this is a precondition. What's happening to the value of the numerator as x gets bigger and bigger? Well, the value of 2x simply gets bigger, so this part is approaching infinity. On the other hand, the value of cosine 3x is going to stay small. Specifically, cosine 3x always stays between positive 1 and negative 1. If this term stays small, something between 1 and negative 1, while the first term gets bigger and bigger and bigger and bigger, the overall value of the numerator is approaching infinity. Of course, the denominator is just getting bigger and bigger as x approaches infinity. So the denominator is also approaching infinity. You must write down arrow infinity, but once you've done that, you can do L'Hopital's rule. By the way, I'm going out of my way not to write 0 over 0 or infinity over infinity. These are not valid expressions, and you will lose a point if you use them. So use arrow 0, and arrow infinity to avoid this. L'Hopital's rule says we can now take the derivative of the numerator and the derivative of the denominator without changing the limit. The derivative of 2x is 2. For the derivative of cosine x, we have to use the chain rule. First, we take the derivative of the outer function, and the derivative of cosine is negative sine. The inner function is the 3x, but then the chain rule says we have to multiply by the derivative of the inner function, so we multiply by 3. The derivative of the denominator is 2x. So let's re-evaluate what's happening to the value of the numerator and the value of the denominator. The denominator is approaching infinity as x gets bigger and bigger. But what about the numerator? I'm just going to say that the numerator stays small. Just like cosine x, sine of 3x stays between positive 1 and negative 1. 2 is a constant. So, multiplying by 3, this part stays between positive 3 and negative 3. So, the numerator fluctuates, but it stays small, while the denominator gets bigger and bigger and bigger. So, the overall value of the fraction is going to get closer and closer to 0. If the numerator stays small, while the denominator gets big, the fraction approaches 0. So that's it. That's the limit. I should mention that when we do L'Hopital's rule, notice we are not doing the quotient rule. This is not a low-d high less high-d low, draw the line and down below, the bottom squared will go situation. We are taking the derivative of the numerator and the derivative of the denominator, and that's it. Pause the video and try to find these first two limits by yourself. L'Hopital's rule may or may not apply. We begin with direct substitution. When we plug pi in for x right here, we get pi minus pi. So the numerator is approaching 0. If you plug in pi for x in the denominator, we have the cosine of pi. Cosine is the x value on the unit circle, and at pi radians, the x value is negative 1. So the denominator is approaching negative 1. 0 over negative 1 is 0. So that's the limit. For the next one, we are finding the limit as x approaches infinity. So we can't just do direct substitution, we have to think about it a little bit. The numerator is a constant, so that's just going to stay a 4. In the denominator, we have to decide which term matters most. The x to the third power, the higher degree term, is growing much faster than the linear term, so we can safely ignore the negative 5x as we think about the limit. X to the third power is increasing without bound as x approaches infinity, so the denominator is approaching infinity. If the numerator stays a 4 while the denominator gets bigger and bigger and bigger, the overall value of the fraction gets smaller and smaller and smaller, closer and closer to 0. So that is the limit. Pause the video and try this one by yourself. Direct substitution gives 0 over 0. So we can use L'Hopital's rule, but make sure you show the arrow 0, arrow 0. This is mandatory for L'Hopital's rule. According to L'Hopital's rule, we can take the derivative of the numerator and denominator without changing the limit. The derivative of the denominator is 1, so you can see why L'Hopital's rule makes things a lot simpler. As I look at the square root of 4x, I'm thinking 4x to the 1/2 power. So here comes the chain rule. I'm going to take the derivative of the outer function, which is 1/2, and then negative 1 power. The inner function is 4x, and we have to multiply by the derivative of the inner function, which is 4. 1/2 times 4 is 2, which I put in the numerator. 4x to the negative 1/2 power is 1 over the square root of 4x, so the limit simplifies to this. Let's try that direct substitution again. We have 2 over the square root of 4 times 9, so that's 2 over The square root of 36 is 6, and this simplifies to 1/3. This is an overview of the strategies that we use to find limits. Most of these we learned back in Unit 1, but now we've added L'Hopital's rule to our toolkit. Now that we know derivatives, many of the problems that we learned back in Unit 1 could actually be solved by L'Hopital's rule. It's very powerful. We cannot find this limit using techniques that we learned back in Unit 1. As x approaches 0, this factor is clearly approaching 0, and back in AP Pre-Calculus, we learned that the cotangent function looks like this. So as x approaches 0, cotangent is approaching infinity or negative infinity. So what do? At the beginning of this lesson, I reminded you that 0 times infinity is not 0. This is an indeterminate form. This is a keep going type situation. We would love to use this new tool called L'Hopital's rule, but L'Hopital's rule is only set up for when we have the limit of a rational expression, something that's in the form of a fraction. However, since cotangent x is just 1 over tangent x, then this expression can easily be rewritten as a fraction. Direct substitution gives 0 in the numerator, and the tangent of 0 is also 0. So L'Hopital's rule does apply. We can take the derivative of the numerator and denominator without changing the value of the limit. The derivative of x squared is 2x. The derivative of 3x is 3. And the derivative of tangent x is secant squared x. This is just a memorized rule. So let's try that direct substitution business again. Plugging in 0 for x, this term is gone, so we have 3 in the numerator. So what is the value of secant squared 0? Our thought process is that the cosine of 0 is equal to 1. Secant is the reciprocal of cosine, and the reciprocal of 1 is still 1. Secant squared will just be 1 squared, which is still 1. So that's why this is 3 over 1, which is simply 3. I would love to use L'Hopital's rule to solve this problem, but first we need to rewrite this expression as a fraction. Since sine is 1 over cosecant, one way to rewrite this as a fraction is to write it as x over cosecant 1 over 4x. But there is another option. X is equivalent to 1 over x to the negative 1 power. In other words, we can take this x and drop it down to the denominator if we make it x to the negative 1. So which rewrite do we use for L'Hopital's rule? It's not always going to be obvious, so be prepared to do a little bit of trial and error and just see which one works best. In the blue expression, the numerator is approaching 0. As x approaches infinity, this fraction on the inside is approaching 0. And the cosecant of 0 is undefined because there's an asymptote there. This is approaching infinity. So we have infinity over infinity, so we can do L'Hopital's rule. L'Hopital's rule says we can take the derivative of the numerator and the denominator without changing the limit. The derivative of x is 1, and using our memorized rules, the derivative of cosecant x is negative cosecant cotangent, but we do have to do the chain rule. But let's start with negative cosecant cotangent. That's the outer function, but then the inner function is this 1 over 4x, which I'm going to write as 1/4 x to the negative 1 power. We have to multiply by the derivative of this inner function, which is negative 1/4 x to the negative 2 power. Well, this is a big old mess, so I'm not liking this one. So let's jump over and see if the red one would work out any easier. First of all, as x approaches infinity, the fraction on the inside is approaching 0, and the sign of 0 is 0. So the numerator is approaching 0. What about the denominator? X to the negative 1 power is 1 over x. So I'm going to just do a little rewrite to make this more obvious. As x approaches infinity, this fraction is approaching 0. We have 1 over something that's getting bigger and bigger and bigger, so the fraction itself is getting smaller and smaller and smaller, closer and closer to 0. So we do have that arrow 0 situation. So I'm going to drop down here where I have more space. This is mandatory. Make sure you show your little arrow 0 before you apply L'Hopital's rule. By the way, notice that I rewrite 1 over 4x as 1/4 x to the negative 1 power. Let me emphasize that 1 over 4x does not equal 4 times x to the negative 1 power. This is a common mistake that I will see students make. Students understand that we are taking this x and bringing it out as a negative 1 power. But they often believe that the 4 and the x are sort of connected. So they want to bring them both out together. But these are not connected like that. The x comes out all by itself. The 4 doesn't go anywhere. The 4 just stays in the denominator. So the x comes out and it becomes 1/4 x to the negative 1 power. Anyway, L'Hopital's rule says we can take the derivative of the numerator and denominator without changing the value of the limit. For the numerator, we will need the chain rule. The derivative of sine is cosine. And then we've got this inner function of 1/4 x to the negative 1 power. The chain rule demands that we multiply by the derivative of this inner function. So moving that negative to the front, we have negative 1/4 x to the negative 2 power. The derivative of x to the negative 1 power is negative x to the negative 2 power. But then we notice that we have this common factor of x to the negative 2 power in the numerator and in the denominator. In fact, they both have a negative. So this cancels out, leaving behind the 1/4, which I will put in the front. And I'm putting this back to 1 over 4x to make it easier to perceive what happens next. As x approaches infinity, the denominator here gets bigger and bigger and bigger, so the overall value of the fraction is approaching 0. So this limit will equal 1/4 times the cosine of 0. The cosine of 0 is 1, so this is just 1/4. And that is the limit. Sometimes we have to do L'Hopital's rule more than once. Direct substitution gives 0 over 0, which you must show by arrow 0, mandatory, but we can move on with L'Hopital's rule. Let's take the derivative of the numerator and the derivative of the denominator. The derivative of x to the third power is 3x squared. The derivative of negative 6x squared is negative 12x. Be careful, for some reason students have a really hard time taking the derivative of a trig function with an exponent. So to be clear, tangent squared x is tangent x, and then that whole thing is being squared. So we have to do the chain rule to take the derivative of tangent squared x. First, we take the derivative of the outer function by moving that 2, to the front, like shmeh. And then the inside function is tangent x. The derivative of tangent x is secant squared. So we have this. However, direct substitution gives us 0 over 0 again. Tangent of 0 is 0, so this factor is 0. The secant of 0 is 1. So, we end up with 0 times 1, which is 0. This means we have to keep going by doing L'Hopital's rule again. So let's take the derivative of the numerator and the derivative of the denominator. This will not change the value of the limit. The derivative of 3x squared is 6x. The derivative of negative 12x is negative 12. Now for the denominator, be careful. This is a product. Do not try to just take the derivative factor by factor. When you have functions that are being multiplied together, the product rule is mandatory. So I'm going to consider the 2 as part of the yellow factor, and then the blue factor is the secant squared. So according to the product rule, we sort of go through this twice. The first time through, we take the derivative of the first factor, the yellow. So I'm bringing down that 2, and memorized rule, the derivative of tangent is secant squared. The first time through, we leave the blue factor alone, unchanged. So I'm bringing down my secant squared x. And then you put a plus, and you go through it again. The second time through, you leave the yellow factor unchanged. So there's your 2 tangent x. But you multiply by the derivative of the blue factor, the second factor. Again, when you have a trig function with an exponent, you have to think of it this way. We have secant x and the whole thing is being squared, so we do have to use the chain rule. First we take the derivative of the outer function, which is 2 times parentheses, where the inner function is the secant x. The chain rule demands that we now multiply by the derivative of this inner function. Memorized rule, the derivative of secant x is secant x tangent x. So that is the derivative of the denominator. Let's see about that direct substitution. If we plug in 0 for x in the numerator, it leaves negative 12. So good news, we will not be doing L'Hopital's rule again. Whatever happens now, we are getting an answer. Keep in mind the following facts. The cosine of 0 is 1. Therefore, the secant of 0, which is the reciprocal of cosine, is also equal to 1. So therefore, secant squared 0 is also equal to 1. We're just squaring 1. So if you do direct substitution and plug in 0 for all of these x's, everywhere you see secant squared, that's going to be a 1. And everywhere you see secant, that's going to be a 1. Also, the tangent of 0 is 0. So when you plug in 0 here and here, you're going to get 0 for these factors. Multiplying by 0 is going to wipe out all of this. So this part is going to just be 0. And then these are both 1s. So we just really have 2 plus 0, which is 2. So it comes down to negative 12 over 2, which is negative 6. And that is the limit. How are we going to evaluate the limit of a rational expression minus another rational expression? If you try to do direct substitution, the natural log of 1 is 0. So don't think of this as equal to 0, but like approaching 0. So the denominator is getting closer and closer to 0. So we have 1 over like 0.000001. When you divide 1 by a smaller and smaller, infinitely small number, the value of this fraction actually gets bigger and bigger and bigger. So infinity. So this fraction is approaching infinity. Similarly, if you plug in 1 right here, you have 1 minus 1, that's 0. But it never is equal to 0. We're approaching 1. So it's the same situation all over again. This is getting smaller and smaller, like 0.00001. But again, this is approaching infinity. So if you understood all of that, you might think that infinity minus infinity is 0. Infinity is not a number. You cannot do algebra with infinity. So infinity minus infinity does not equal 0. This is an indeterminate form. This is a keep going type situation. In general, when you see a fraction minus a fraction or a fraction plus a fraction, your instinct should be to combine these into one single fraction by forming like denominators. So let's multiply the fraction on the right by natural log x over natural log x to help get like denominators, and let's multiply the fraction on the left by x minus 1 over x minus 1. Got to squeeze it in there. And now we have like denominators. Combining the new fractions over the common denominator gives us this. If we do direct substitution, plugging in 1 for these x's, we have 1 minus 1, so that's 0, and the natural log of 1 is 0. So same thing down here. This is 0 times 0. We have now learned that when direct substitution gives you 0 over 0, you are allowed to use L'Hopital's rule. This is mandatory. Make sure you show your arrow 0 before applying L'Hopital's rule. L'Hopital says we can take the derivative of the numerator and the denominator without changing the limit. The derivative of x is 1. The derivative of negative 1 is 0. And memorized rule, the derivative of natural log x is 1 over x. When you get to the denominator, do not think that you can just take the derivative of each factor. This is a product. So you must do the product rule. The first time through, you take the derivative of the yellow factor, which is 1 over x. And you leave the blue factor unchanged. And then you put a plus. The second time through, you leave the yellow factor unchanged, and you multiply by the derivative of the blue factor. But that's 1, which we don't really need to write. Let's try direct substitution again and see what we get. If we plug in 1 right here, that's 1 over 1, which is 1. So in the numerator, we have 1 minus 1, which is 0. In the denominator, we have 1 minus 1, so that's 0. So this factor is gone. And the natural log of 1 is also 0. So this is a keep going situation again, and we can again use L'Hopital's rule. We can take the derivative of the numerator and the denominator without changing the value of the limit. The derivative of 1 is 0, and I'm bringing down this negative sign. When I take the derivative of 1 over x, I'm thinking of it as x to the negative 1 power. So that negative is going to come to the front and turn this positive, and then I will have x to the negative 2 power as I reduce that exponent by 1. When I get to this part right here, I again must be very careful. Don't just think you can take the derivative of the red and the derivative of the blue. This is another product. So we have the yellow factor times the blue factor. The product rule is not optional. The first time through, we take the derivative of the yellow factor, and the derivative of this is negative x to the negative 2 power. We leave the blue factor unchanged, so x minus 1. And we put a plus and go through it again. The second time through, we leave the yellow factor unchanged, and we multiply by the derivative of the blue factor, but that's a 1, which we don't need to write. So there's your product rule. We still need to take the derivative of this last term, and that's 1 over x. Let's see what happens if we do direct substitution now. Plugging in 1 for x right here. 1 to the negative 2 power is 1, so the numerator is approaching 1. Focus on this factor. 1 minus 1 is 0, and so this factor, this term, is going to be 0. So that's gone. So what's left is 1 over x plus 1 over x. If we plug in 1 for these x's, this is 1 plus 1, which is 2. So that's it. The limit is 1/2. Pause the video and evaluate these two limits on your own. You might or might not use L'Hopital's rule. For this first one, direct substitution gives us 0 over 0, which you must show, so we can do L'Hopital's rule. The derivative of the numerator is 1, and the derivative of the denominator is 2x. If you do direct substitution now, you get 1/2. Easy peasy. You also could have done the factor and cancel method that we learned back in Unit 1. Same answer. When you do direct substitution plugging in 0 right here, 3 to the 0 power is 1, so we have 1 minus 1, which is 0. Of course, if x is approaching 0, the denominator is approaching 0. You have to show this, but we can do L'Hopital's rule. We can take the derivative of the numerator and denominator without changing the value of the limit. Here's a memorized rule that students often forget, so bust out those flashcards and write this down and study it. The derivative of a to the x is equal to a to the x times the natural log of a, where a is any constant other than 0. So the derivative of 3 to the x is 3 to the x, but also times the natural log of 3. The derivative of -1 is 0, so that's gone. The derivative of x is 1. So we really just have what's in the numerator. Doing direct substitution, if we plug in 0 for x, we have 3 to the 0, which is 1. So that leaves the natural log of 3. That's the limit. One more time, pause the video and try to evaluate both of these limits on your own. As x approaches infinity, cosine x oscillates between +1 and -1 forever. So it stays small, always between -1 and +1. In AP Pre-Calculus, we learned that the graph of natural log x looks like this. So as x increases without bound, natural log x approaches infinity. If the numerator stays small while the denominator gets bigger and bigger and bigger, the value of this fraction gets smaller and smaller and smaller, closer and closer to 0. So that is the limit. If we attempt direct substitution on this problem, we really can't, because the natural log of 0 is not defined. So we really have to think about it. Well, I mean, the first factor, sure, that's just 0. But what's happening to the natural log of x as x approaches 0 from the right? As x approaches 0 from the right, the value of natural log x approaches -infinity. It's falling and falling and falling. So we have 0 times -infinity, which is not 0. Okay, because this is not actually 0, we are approaching 0. So this is more of a battle. This factor is getting smaller and smaller, well, closer and closer to 0, while this factor is getting more and more negative. It's getting bigger and bigger in absolute value. So it's a matter of sort of which one's going to win. The bottom line is this is a keep going situation. This is an indeterminate form. I'm hoping I can find this limit using L'Hopital's rule, but I will need to rewrite this as a fraction. Think of x as 1 over x to the -1 power. In other words, we can drop this x down to the denominator as long as we make it x to the -1 power. Again, as x approaches 0 from the right, the value of natural log x approaches -infinity. X to the -1 power is really 1 over x. You can't just do direct substitution and plug in 0 because 1 over 0 is simply undefined. So you have to picture what happens to the value of this fraction as x gets closer and closer to 0. Imagine 1 over 0.1 and then 1 over 0.01, 1 over 0.00001. As the denominator gets closer and closer to 0, the value of this fraction is getting bigger and bigger and bigger. 1 divided by 0.00001 is actually a really big number. So, as x approaches 0 from the right, x to the negative 1 power approaches infinity. This counts as infinity over infinity for L'Hopital's rule. We can take the derivative of the numerator and denominator without changing the value of the limit. The derivative of natural log x is 1 over x. That's a memorized rule. For the denominator, we use the power rule, so that's going to be negative x to the negative 2 power. Let's rewrite x to the negative 2 power as 1 over x squared. So that means we have a fraction divided by a fraction. Therefore, we multiply by the reciprocal. In this form, we can see that this x in the denominator will cancel out one of these x's. So we have the limit as x approaches 0 from the right of negative x. Direct substitution gives us 0. So that's the limit. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.